In this video we will start our applications of integration, the first of which is the area in between two curves. So if you remember that the definite integral of f of x dx has a geometric meaning, and this is the signed area under the curve. And another way that we could represent this signed area under the curve is it's also the area that is trapped between f of x, the function, and the x-axis, because everything was related to the x-axis when we did dx integration. So the question now is, let's say that we have two functions. Let's say that we have f of x in blue, here it is, and let's say that we have g of x in red, like this. And what we want to do is we want to find the green area, which is trapped in between g of x and f of x. Let's say, and then, alright, so g of x and f of x have two intersection points. Here's one and here's the other. And those two things, those are going to be the a and b values that we're going to use to set up our integral. So let's think about this. Well, we know that if we were to integrate a to b of f of x dx, this would give us this blue area. Try to shade this in nicely. So it gives us this blue area, which is all of the area under f of x, between f of x and the x-axis. But that's not what we want. We want to, we've overcounted area, so we need to take back area. And so you can think about subtracting, if we subtract the area under g of x, like this, then what we're left with is this like oblong, oval-shaped region. That was what we were starting for. So the idea here is that the original green region, which we started with, will be equal to the the integral of f of x from a to b minus the integral of g of x dx from a to b. And now this is going to be a lot easier to think about if, notice that we have the same units here, sorry, not the same units, but the same limits of integration. Because we have the same limits of integration, we can rewrite this equation as this. The integral from a to b of, in this case we had f of x minus g of x dx. And this is the area between two curves. Now, before you get all excited and put big boxes and squiggly lines around this and be like, yay, we're done, just be forewarned that this is not a catch-all formula. If you would like a catch-all formula, I would recognize this one as the catch-all formula for area between two curves. Specifically for a dx integration, the best formula, or the way to think about the area between two curves, is to just take the top function and subtract the bottom function. And the reason is because, well, what if we came up with a situation where g of x was on top and f of x was on the bottom? You'd have to remember to switch them, and that, like, if you're using the f minus g formula, it just gets all complicated. So just think about it. Hey, g of x is on top here, f of x is on the bottom, so this one you're going to use g of x minus f of x and then go from there. Let's do an example so this makes sense. Let's say we want to find the area bound by f of x equals x and g of x equals 2 minus x squared. This phrase bound by basically means trapped between. This is common language that shows up when we do these problems. So we're probably going to use our formula, which is, you know, a to b of top minus bottom dx. And now we need to figure out which function is on top and which function is on the bottom. So yes, you do need to know some of these graphs. So the graph of f of x equals x, pretty straightforward, because it's a straight line, so it's straightforward. Never mind. And then the second equation, g of x, I'll draw it in red, is 2 minus x squared. So this is a parabola that's opening downwards, and it's been shifted up 2 units. So we're starting here, and then opening downwards like this. Can you spot the region? I can. It's this green region that's trapped between the two graphs. Excellent. So we need to do a couple things. First of all, which function is on top for the region? And if you see clearly, g of x is on top. So our integral will be the integral from a to b of g of x, which is 2 minus x squared, minus the bottom function, which is in black, which is x dx. Now, this is something that you should do just out of habit, but the second function, always put these in parentheses. And the parentheses are good because that helps you remember that, oh, there's a negative here and you need to distribute, wow, that was a terrible letter and stuff. Distribute the negative. So always put parentheses there. It will help you remember to do that. Well, the nice thing about this is we're almost done setting up the integral. The last thing that we need to do is we need to figure out the intersection points in order to determine the limits a and b for the integral. So think for a second about how to do that. Great. The best way to do this is to find where the two functions intersect. Notice that these are special points because that's where the functions intersect. So to find those points, we're basically just going to set the two functions equal to each other. We do f of x equals g of x. And then we're going to solve this equation. So if I add x squared to the other side and subtract 2, I'll get x squared plus x minus 2 equals 0. Factoring gives us x plus 2, x minus 1 equals 0. And so my two solutions for x are negative 2 and positive 1. Therefore, the lower limit of integration is negative 2, and the upper limit of integration, is 1. Hooray! Now we can do the integral. The integral that we have is negative 2 to 1 of 2 minus x squared minus x dx. I'm going to do this rather quickly, so stay with me. The antiderivative will get 2x minus x cubed over 3 minus x squared over 2, evaluated from negative 2 to 1. So now we plug in 1. We're going to get 2 times 1 minus 1 cubed over 3 is 1/3, minus 1 squared over 2 is 1/2, minus, simplifying as we go, 2 times negative 2 is negative 4. Negative 2 cubed is negative 8, divided by 3 is 8/3, and then the negative and the negative will cancel and become a positive 8/3. Negative 2 squared is 4, 4 over 2 is 2, and the negative stays there, so this is a minus 2. We're going to distribute this negative, that's why you have to be careful with your parentheses. So you have 2 minus 1/3 minus 1/2 plus 4 minus 8/3 plus 2. Combining the whole numbers, we're going to get 8. Notice here that minus 1/3 and minus 8/3 is minus 9/3, which is minus 3. So we have 8 minus 3. And then we have the very lonely 1/2 that's left over. 8 minus 3 is 5. 5 minus 1/2 is 9/2. So that is your answer. This is the most time-consuming part of the thing because you have to calculate it, but this is the key here, is setting up this integral. Some common variations of the area between two curves problems. One of them is that oftentimes the problem will give you the limits of integration. So it'll give you the a value and the b value, probably as x values, and that will help you because then you don't have to find the intersection points. Going the other way, you could have a section or a problem where instead of 2 intersection points in one region, you have 3 or more intersection points in 2 or more regions. An example of that would be, here's the function f of x, and the function g of x goes above and below f of x. So let's label these f, here's g. You would have to find, let's see, 1, 2, 3 intersection points, so let's call this x equals a, b, and c. And then you'd have to set up 2 integrals to do this. The first integral would be this first region, and that first region would be the integral from a to b. G is on top here, so we're going to do g minus f dx. And then we're going to add the second area. And notice that the second area, f is on top, so we have to set up a new integral, the integral from b to c of f minus g dx. And then you would have to calculate each of these separately and then add them to get the new integral. And so it's very important, you need to be very aware of the fact that you're doing top function minus bottom function, otherwise you'll get it wrong. There is one more variation that will be covered in a new video.